Okay. Good evening to everyone in India, and good morning to the people in US, and good afternoon probably in people in Europe. So welcome to the Special Functions and Number Theory seminar. Again, we are resuming it from this semester with a talk by Professor Dennis Stanton, and he'll be talking on some open problems in Q series, partitions, orthogonal polynomials, and special functions. So over to you, Professor Stanton.
Thank you very much, Atul, and thank you for the invitation to talk. Particular Gaurav for inviting me. I have not met Krishnan Raj Kumar, but you two I've known for a long time, so it's nice to see you again. Let me start with, how do I advance the page from this? You know how to advance the page?
I think just try page down, just the arrow.
Arrow does not work.
Is it on an iPad?
No, this is just
Oh, there we go.
okay.
Okay, apparently I'm going to have two pages at once, but that's okay.
Yeah.
So here's an outline. My first topic is going to be some open problems with Rogers and Ramanujan identities. Then I'm going to talk about type 1 orthogonal polynomials. And finally, at the very end of the talk, we'll just have a sorted probability, positivity problems. I believe I've written down 10 problems to work on for this talk. And you can see some of these problems on a paper on my webpage called Open Problems from the year 2019. And there are other problems there too. They're not on the archive. Okay, first topic, Rogers and Ramanujan. Where here we have on the right the first and the second Rogers and Ramanujan identities. A Q series sum equaling a Q series product. And if you notice on the right-hand side is the generating function for a certain set of partitions. The first one is a set of partitions where
একটা ভিডিও দেখছি অঙ্কের ভিডিও
But the first part is the right-hand side, partitions whose parts are 1 or 4 mod 5. And McMahon figured out the combinatorics of this left side. He said it's partitions, generating function partitions of n, whose difference is at least 2. So the parts are distinct and they have to differ by 2. So a partition that would be okay would be like 7 plus 3 plus 1. But 7 plus 6 plus 2 would not be allowed. And I'm going to use throughout this talk this notation from Q series, A base Q sub n. Any questions about the notation? So this number 2 begins 1 plus Q squared over 1 minus Q plus Q to the 6th over 1 minus Q, 1 minus Q squared, etc. So we're going to need to remind ourselves how McMahon got that left side. Partitions with parts differing by at least 2. What he did is he took such a partition, here I've written its Farrer's diagram, and he stripped away the double staircase, 1, 3, 5, up to 2n minus 1 if it has n parts. And that what remains is just an arbitrary partition whose parts could be any numbers from 1 to n. So if you look down here, it's Q to the sum of the double staircase, any partition whose parts are 1 up to n. So that's the Q to the n squared over this factor. Now this theorem has appeared all over the place. Here are some places There's an algebraic proof of this identity in representation theory of the algebras, statistical physics, knot theory, symmetric functions, and root systems. And there are versions of this theorem for all moduli, not just mod 5. For higher odd and even moduli, you start getting multiple sums instead of a single sum. Unknown, even today, is a direct bijection for McMahon's version. If you look at McMahon, this thing right here, the fact that these two integer partition sets are the same in number, there's no explicit bijection. There's an implicit bijection by the so-called involution principle. So for this talk, I want to talk about weighted versions. I want to put some weights on the partitions. Well, one way to do it would just to put in a little t to the n here on the sum. So you would weight the difference two partitions by t to the number of parts. That's what this would be. Since q to the n squared over q sub n was for n parts, just put in a little 2 to the n. What happens on the product side when you do that? Well, this is Watson did this. Watson, in his proof of the Rogers-Ramanujan, changed that product sign into an alternating sum. And then when t was equal to 1, that alternating sum factored by the Jacobi triple product. So it actually canceled down to the infinite product we have on the right-hand side. But you don't get an infinite product, you get an infinite sum. The first problem today is based on this problem. Suppose I put a little t in the product side, say on just one single term. This means any part of size 2 would be weighted with the t. So if you had 12 2s, it would be t to the 12th. What happens to the sum side when I do that? Does everyone understand what the problem is? Well, we have an answer for that. We can tell you what happens to the sum side and where does the 2 show up over here on this picture? We had 12 2s. Here it is. This is a theorem I did with Kathy O'Hara. Here's the sum side now. The 2 shows up right here in the columns of size 2. That's nice. And then it shows up right here. This term, the first term, is when you have only one part. And so basically, this t goes with this q squared, or this t goes with this q squared. If you have a part, you take t to half the part, basically, when you have a single part. So it's just what you'd want. The 2s change into 2s, plus something funny happens with the parts of size 1. Parts with one part. And in particular, you can figure out what happens in Rogers-Ramanujan when you don't have any 2s. Just put t equals 0. No 2s. Then you don't have any 2s over here. And here, this is gone. And this, you just have q cubed. The only partition. This is with difference 2, smallest part at least 2. It's the second Rogers-Ramanujan. Well, it's easy to figure out what it means when t equals 0. What happens if I put a t not on the 2, but on any of these terms down here? Well, something very similar happens. In the sum, it's very nice. This, if the terms are past where you insert the t, they just insert exactly as you would hope. The earlier terms, though, are completely changed. In particular, if you look at the second part here, this last part, when t equals 1, is 1 over 1 minus q. These are the ones. These are the ones when you strip away the double staircase. In other words, it tells you about the length of the largest part. And so instead of having divided by 2, you got to divide by m plus 1, basically, for the largest part. And then there's a little more complicated thing here for the single part partition. Note if t equals 1, this is 1 over 1 minus q. So it's just ones. So the ones, you have to separate them modulo divided by m plus 1 to tell you the power of t. So it's a little more complicated. So how do you prove this theorem? You prove it by an equivalent identity. Let me try to get rid of this. You see, you just multiply usual Rogers Ramanujan by this factor. And then that will kill the m plus 1 and insert the t. So you need to multiply this factor by the sum side of Rogers Ramanujan and get this new sum side. So if you were to divide both sides by 1 minus q to the m plus 1, everything would be positive. They would all be positive. And so to prove this theorem is equivalent to proving this rational function identity. Okay, what happens for more? Well, you may not be able to see this theorem. I didn't want to write it out by hand. As you can see, there are many, many terms. Let me see if I can zoom in. Uh-oh. I can zoom in on that. Let's see if I can go backwards. See, I want to go backwards. How do I go backwards? Oh, there we go. Let's zoom in. So here's what happens if you try to insert different parameters for 2, 3, 7, and 8 when you're doing the second Rogers Ramanujan. With T, W, V, and X. This is what you get. Now notice the first term, which should have been q squared over 1 minus q, now has this t plus wq over 1 minus t squared. And the next term, which should be q to the 6th over 1 minus q1 minus q squared, well, you've got q cubed and q to the q squared, which looks like it's going to be a 3 and a 2, but there's 3 terms on the top. So these 3 terms on the top combine with the second factor to be like 1 over 1 minus q. And every single term, this next term should be 1, 2, 3. Well, instead I have 7 terms over 2, 3, 7. So it's like a 1, 2, 3. All the terms are positive. Here's something that should be something over 1, 2, 3, 4. I have now 2, 3, 8, 7, with all terms positive. And here's the next term. All terms positive. All terms positive. And once you finally get past 8, these T, W, X's, and V's are exactly what you'd hope them to be. They fit in exactly as columns. But before 8, some strange things are happening. And it's important that all the numerators are positive. There's no cancellation. It is possible to write down the combinatorics of this. So here's problem one. Is there an explanation for the underpinning positive rational function identity? So it looks like some generating function for some modules. You have some rational function equals another rational function with positive numerators. I'd like to find out what this is. And I'd also like to try to, if possible, go farther. Is there an infinite series positive version? I don't know about that at all. In fact, the version I showed you with 4 factors is not unique. I found another one too. So that's troubling. When it's not unique, it may mean it's very hard to find. Well, one thing you can do with this is, besides letting the parameters equal 0 and killing terms in Rogers-Ramanujan, you can let the parameters be powers of Q. So for example, you can change a part of size 2 in the second Rogers-Ramanujan to like a 9 by letting t equal q to the 9th, t equal q to the 7th. So changing a q squared into a q to the 9. So you get theorems of the sort Rogers-Ramanujan with certain things shifted out equal certain kind of difference conditions on partitions. Does everyone understand this first problem one? Okay, let's go to the second topic with Rogers-Ramanujan, and this has to do with Schur functions. So the Schur function is a symmetric function S lambda in infinitely many variables. Lambda is a partition of n, and the x's are arbitrary parameters. So it's like a polynomial of degree the size of lambda, but it's like an infinite polynomial. It's symmetric. And these Schur functions have this Cauchy identity, which is a generating function for S lambda x and S lambda y as a 1 over a product, 1 minus xi yj. What's good about this is that there's a straight bijection that proves this, called the Robinson-Shenstedt-Knuth correspondence. It takes pairs of things at these Schur functions, which have positive coefficients count, and produces words, which is what the right-hand side count. Everybody's positive. So what do the Schur function count? They count column strict tableau of shape lambda. So here I've written one. If lambda is a partition 3, 1, then here's a column strict tableau P. The first row numbers increase weakly, and down the columns they increase strictly, column strict tableau. And the weight of this is this monomial, 1x, 1, x1, x3, x4 squared. So let's choose some x's and y's. Let's choose the x's to be q to 5 times an integer, and let's let all y's be only two possible things, a q and a q to the 4th. Then that product side, let's go back and look at it. The x is a q to the 5th. Let's look at it right here. And the y's are either 1 or 4. Well, you get the product side of Rogers-Ramanujan. You get 1 mod 5 and 4 mod 5. And so That's exactly what we want. And the sum side is now a generating function for pairs of column strict tableau, P and Q. And they have to have at most 2 rows because the Y alphabet has only 2 letters, a 1 and a 4. And you've got to be column strict. You can't have 3 rows and have 3 distinct numbers there because you only got 2 numbers, a 1 and a 4. So that's a pretty good thing. These column strict tableau with 2 rows or only 1 row. So we know there's a bijection now between the product side of Rogers-Ramanujan and these pairs of column strict tableau. So this is problem 2. Rearrange these pairs of column strict tableau to obtain the sum side. And if you do that, you'll have a McMahon bijection. There's no minuses anywhere in this. Everything is strictly positive. The very first step is Robinson-Jensen-Knuth. So now there's just some rearrangement. So in fact, I did this for n up to the first 2 terms, I think, here. Maybe the first 3 terms in this sum. I found the P's and the Q's that would work to give the first 3 terms. But it's a big mess. Too hard for me these days. I don't see how to do it. Maybe with ChatGPT or some other clever device, you might be able to do this, and you'll solve this problem of McMahon. You know, that's been a big problem that no one's been able to do for a long time. So if you want to read about this, I wrote a tiny blurb about it. It's on my webpage. I wrote a blurb about it last year. In fact, I wrote that for Steve Milne. Okay, any questions about this problem? That's problem number 2. And now we come to problem number 3, which is also on Rogers-Ramanujan. And one thing that I had wondered about for a long time was, is there a quintic transformation, something that changes a Q series on Q to the 5th into a Q series on base Q that will give Rogers-Ramanujan? Be a quintic transformation, Q going to Q to the 5th. And yes, I did find such a thing. Oh, there's some variations. You can actually try to do the Borwein problem with this too, by doing the dual Cauchy identity. So I think this is an area people haven't looked at, to use symmetric functions to do some of our conjectures. The dual Borwein will have some minus signs, which it has to have. So here's this quintic transformation. Look at this theorem. The left side is the same thing Watson had, basically. Just insert a power of t. The right side now is a 3phi2 on base q to the 5th. And the t's are everywhere, it seems. There's t's all around everywhere. It's not all positive. Notice if t squared is, it looks like 1 over q squared, that 3phi2 is 1, and then we have 3 factors base q to the 5th over 1 factor base q. Those 3 factors will cancel, and you'll get the product side of Rogers-Ramanujan. Similarly, this one, this 3phi2 actually equals this 3phi2 by a 3phi2 transformation. And this time a t squared is 1 over q. Well, t squared is 1 over q. You get a 6, a 5, and a 4, pod 5. And the bottom gives you a 2. So the 1 is missing. That's why it's a 6. And, ooh, this should be a 4 and a 5. Yeah, you'd have a 1, 4, 5 canceling. So you're left with 2 and 3. That's the product side of Rogers-Ramanujan. So this identity gives Rogers-Ramanujan. And in fact, when we did it, we don't have to do the Jacobi triple product either. It's kind of built into these transformations. You still need to do cancellations though. So this is problem 3. Find another proof or maybe a generalization of this via basic hypergeometric series. The only proof I know of this uses orthogonal polynomials and some integrals and some Q-Hermite polynomials. I don't know a proof using just classical basic hypergeometric series. And if there is such a proof, you might think this side right here where this q to the n squared is some sort of confluent limit. Maybe there's a better theorem around. And really there should be 2 factors on top and a factor on the bottom, and not that q to the n squared. I don't know. I don't know what that theorem should be. That's problem 3. And Michael Schlosser has this bilateral Rogers-Ramanujan. Is there a quintic transformation for that? I don't know. I think this problem is probably doable, but it's a mystery to me right now. Any questions about problem 3? Okay, we're now leaving the Rogers-Ramanujan problems and we're going to type 1 orthogonal polynomials, type R1. So for me to tell you what those things are, these type R1 things were defined by Morad Ismail and David Masson in 1995, and they just kind of sat there and not much happened with them for like almost 30 years. We need to review orthogonal polynomials. So let's review orthogonal polynomials. We have a monic polynomial in X, degree n, and it satisfies this 3-term occurrence. Pn plus 1 is x minus bn pn minus lambda n pn minus 1. So for example, the Hermite, Laguerre, Jacobi polynomials are examples of usual orthogonal polynomials. The theorem is this. There is some linear functional on the vector space of polynomials such that the linear functional applied to the product of the p's is 0 for different degrees, and it's non-zero. It's a product of the lambdas if they're equal. Now, you might want to think of the linear functional as integrating with respect to a measure. So L of a polynomial is integrate the polynomial. And it is true that if B is real, Bn is real and lambda n is positive, then there is a positive measure for which L is equal to this. But the measure may not be unique. There could be more than one measure which has the same set of moments. So that's the review of orthogonal polynomials. So I'm going to write down the same stuff for type R1. What does a monic type R1 thing do? It adds this extra factor right here, this an of x right there. There's a new factor, x, in the pn minus 1 term. So an equals 0 would be the normal orthogonal polynomial. We're going to assume an is not 0. Same initial conditions. And now the vector space is, besides polynomials, you need these rational functions. 1 over d1, 1 over d2, where the d's come from this factor right here. We use those as multiplying them together to give a denominator polynomial, these dn's. So the vector space now is bigger. So the theorem is take this vector space, there's some linear functional on this bigger vector space, such that L of pk pn over dn is 0. So formally speaking, if the a's are 0, the d's are out, and you would go back to just orthogonal polynomials. So these are called type R1. There's also a type R2, where right up in here, it's a quadratic polynomial in X. So it's degree 2. And the same kind of theorem holds. The D now is a product of quadratic polynomials. Okay, what's an example of this type R1 stuff? Well, maybe before I give an example, let's think about the moments. The moments of this linear functional, L of x to the n, are always positive polynomials in the 3-term recurrence coefficients. And we know the combinatorics of this in terms of lattice paths. That exists. And they can be uniquely determined by this equation. L of Pn is no longer 0, it's a product of the A's. You can do that recursively to find all the moments. And if you want to find L of 1 over dn, you can do that recursively by doing L of Pn over dn. Everything is in terms of the 3-term recurrence coefficients. Okay, here's an example. Let's take the Laguerre polynomials. So here I've written the 3-term recurrence of the Ln alphas, but B is apparently alpha minus 1. So I got rid of alpha and I wrote in B instead. So if you look at this 3-term recurrence, it's an orthogonal polynomial in X recurrence. It's X minus something. That's this factor right here. And then over here, it's independent of X. Well, that's the Laguerre 3-term recurrence. But now think of it as a recurrence in B. It's linear in B here and linear in B here. These Laguerre polynomials are type 1 orthogonal polynomials in the parameter. So they have their OPs in X and their type 1 OPs in B. They have 2 different orthogonalities. In X, the usual integral is, x to the alpha e to the minus x for the Laguerre. It's the gamma distribution. We actually know what the measure is for the type R1 and B. I'll say something about that in a minute. But there are many, many examples of this. So in 2 papers I wrote recently, one with Jiangsu Kim, not Dongsu, Jiangsu Kim, and a paper I did with Morad, many, many classical examples in terms of hypergeometric and basic hypergeometric series. Here's an example of a polynomial that's an R2 polynomial. So it depends upon 5 parameters, T1, T2, T3, T4, and T5. It depends upon Q, some kind of a Q series, and X is cosine theta, Z is e to the I theta, and here it is. It's a 10W9. So it's a very well-poised series. It's not at all obvious this is a polynomial in X. That takes quite a lot of work to prove. It also has the bonus that if T5 is equal to 0, this T is equal to 0, this T right here, that goes away. You'll go down to an 8W7, which is by a transformation of 4phi3. These are the Askew-Wilson polynomials, which have 4 parameters. This thing with 5 parameters generalizes the Askew-Wilson polynomial, and it has an orthogonality relation, very much like the Askew-Wilson. By the way, this paper has only just appeared, but we actually did it around 2010, but it was sort of in limbo for a long time. It's a paper with Eric Range and Morad Ismail. You can find it on my webpage. Here's the orthogonality. So it's an R2 orthogonality. There's the degree 2n polynomial in the denominator. When t equals 0, it goes away completely. You have normal orthogonality. And what you have is this measure. You've got the usual Q-Hermite measure, 1 extra factor on top, and 5 factors on the bottom. The Askew-Wilsons have 4 in the bottom and the Q-Hermite on the top. There's a 1 over 5. One question has always been, why can't you go farther on the Askew-Wilson? Why do you have to have 4 factors there? Well, if you go farther, this is the way to do it. And in fact, we can do an arbitrary number of factors, but you get orthogonal rational functions to the polynomials. So here's the orthogonality. You get 0. It's a type R2 orthogonality. Okay, this all looks very interesting. What are the problems? What's an appropriate R1 10W9 version? Is there one? And is there a corresponding ASCII scheme? The ASCII scheme for basic hypergeometric series has the Askew-Wilson polynomials on the top, and then many, many subcases. Is there an R1 version of the ASCII scheme with some kind of 10W9 on top? And is there an R2 version also? I don't know. We have many, many examples, but I can't say that we understand it very well yet. So this seems to be completely open, and I think it's probably doable once you understand enough. Here's problem 5. There's a theorem called Leonard's theorem in association scheme theory that says bispectral orthogonal polynomials. These are orthogonal polynomials that have a 3-term occurrence and their duals have a 3-term occurrence. So somehow they're polynomials in X, and they're somehow polynomials in some function of n if X is in some kind of an integer. So his theorem from the early 1980s said, classified these bispectral things as limits of Q-Rocca. They're in the ASCII scheme. They have to be these Q-Rocca polynomials. And they all have discrete orthogonalities if there's a finite number of them. Is there a type R1 Leonard's theorem where you, instead of having bispectral orthogonal polynomials, you have bispectral type R1 polynomials? Polynomials have a 3-term occurrence, type R1, and their duals of type R1. Or is there a Leonard's theorem where the polynomials are orthogonal and the duals are type R1, some kind of mixed theorem? I don't know. Well, that's problem 5. Any questions about this problem? Here's an interesting fact. The type R1 moments for Laguerre are the orthogonal polynomial moments for the Charlier. And the type R1 moments for the Charlier, which are also have a parameter, that they become a type R1 polynomial, are the orthogonal polynomial moments for the Laguerre. This is like duality between these two polynomials. The moments for 1 and x equal the moments for the 1 and the parameter. They swap. Well, there are many, many more examples of this in this paper I did with Morad. And we call this thing moment duality. I don't have any idea why this is true. All I can do is compute it and see that it is true. So there's something that we just don't understand about this moment duality. This is problem 6. Is there a general result for moment duality? In fact, I was almost sure that these examples had to be a special case of some very general theorem I just didn't know. I couldn't find the theorem. And is there a map on the ASCII scheme that does duality, that maps polynomials to their duals? I don't know. So this all appears in this paper with Morad called moment duality for orthogonal polynomials. Okay, we have less than 10 minutes remaining. Oh, let me tell you about this. Bonus result. This is really neat. If two sets of moments are the same, then their moment generating functions are the same. And for orthogonal polynomials, you always have a Jacobi continued fraction for the moment generating function in terms of the 3-term recurrence coefficients. So here's the Jacobi continued fraction. Same thing happens for type R1. Their moment generating function has another continued fraction in terms of its 3-term recurrence. You always get this equality of continued fractions when you have moment duality. And the examples I have in the papers, I don't know how to prove this otherwise. So maybe if you're a wizard with continued fractions, you can, but I didn't see how to do it. So as far as I know, these are non-trivial type theorems on continued fractions. Okay, so I'm going to end the talk with a few assorted problems. This problem, the first one, I like this problem. I can't say it's all that important, but I really like it, so I'll talk about it a little bit. So here's a theorem we proved. It's some kind of sum of binomial coefficients where the index differs by a k. So S equals 0, n plus m choose m. Well, since n and m are close, that's kind of the biggest binomial coefficient. And then as S gets larger, you get smaller and smaller binomial coefficients. This times cosine x is positive. And I don't know an analytic proof of this. The only proof I know is a combinatorial proof. I don't know any proof from analysis that proves this. Now, why did I want to do this? Well, if x is equal to pi, then cosine of pi s is minus 1 to the s. And that's this alternating sum of binomial coefficients being positive. And we know what it counts. It counts certain lattice paths. Well, so this theorem occurs in this paper with Dong-Soo Kim and Morad, 1999. What I want is a Q version of this with a q binomial coefficient and maybe a cosine, maybe, I don't know, some q version, I'm not sure. Q to some quadratic power. And I'd like when x equals pi for this positivity to be positivity as polynomials in Q. So it implies Brissoud's generalization of the Borwein conjecture. So the idea is to take Borwein's conjecture, do a generalization of David Brissoud, change it into an analysis-looking problem, which would be this theorem. Now that paper has something that purports to do this, but we didn't prove it in general, and it may be wrong. It may be the wrong thing. I'll just say it has some twisted attempt at this, which may not be the right one. Maybe if you have better insight, you can do it. In particular, we know from partitions with Hooke differences, if you put in a q binomial here and a minus sign and a power of q, it does count certain partitions. That's this paper with the 6 authors, Andrews, Brissoud, et cetera, on Hooke differences. The problem with the Borwein, of course, is that some of the parameters are rational numbers instead of integers, and that theorem doesn't apply. So I like this theorem. I can't say that it's all that important. Good luck on doing problem 7. Let's move to finite fields. Okay, let's think of doing the following. Let's take the cyclic group of order n that acts on the points 1, 2, 3 up to n. It just cycles them around. If it acts on those points, there's an induced action on all the k subsets of n. And what are the sizes of the orbits? Well, the size of the orbit must be a divisor of the size of this group. So it has to be size E, where E times some number D is n. And you can do a Mobius inversion to compute this number. Equal to 1 over E times the sum of a Mobius function times a binomial coefficient, n over s, choose k over s. It counts the number of orbits. What does this have to do with finite fields? Well, there's this theorem of Drudge. This cyclic group of order n, that n cycle in a finite field has an analog called the Singer cycle. It has order q to the n minus 1. And you could let it act on all the k-dimensional subspaces of a vector space of dimension n. We know the total number of subspaces is n choose k base q. The number of orbits now has to be e base q to the d, as it turns out. What do you get as an answer? Looky here. Exactly the same looking, but now you get a q binomial, but now this is base q to the s. And instead of dividing by e, we divide by e base q to the d. It looks exactly the same as this up here. Well, in particular, if n and k are relatively prime, then you're not going to have any s dividing GCD. D is going to have to equal 1. S will equal 1, and you'll just get n choose k over n. That's what's called the rational Catalan number. So that's something that combinatorial people have spent a lot of time studying in terms of lattice paths. So this generalizes that when n and k are not relatively prime. Problem 8. Prove this is a non-negative polynomial in Q. Well, we did prove this is a polynomial in Q, which is not obvious because of this factor right here, this denominator business. So for just the Q binomial coefficient, it's easy to do that for subspaces by taking a basis and writing it in row echelon form. And then where the stars are in the row echelon form gives you a partition inside a rectangle. So there should be some version of that for these orbits, that row echelon form business, but we don't know what it is. Well, you can find this conjecture in this paper I did with Dennis White and Victor Reiner on the cyclic sieving phenomenon from the early 2000s. There's also flagged versions where instead of doing subspaces, you do flags. And there's also type B and type C versions of the Singer cycle, but we didn't study that. So there's going to be some other theorems around too. Okay, here's the last problem. Has to do with alternating sign matrices. These are matrices of 1s, 0s, and -1s, where the non-zero entries in every row or column alternate plus, minus, plus. And every row and column sum is a 1. So permutation matrices are an example of these. And the first one that has a -1 would go across the first row 0, 1, 0, second row 1, -1, 1, and third row 0, 1, 0. So the number of these matrices, this was an open problem for a long time. Doron Zalberger proved this quotient of factorials is the number of these ASMs. Problem 9. Find a statistic on these ASMs so that the Q version of this holds. It's known that this is a polynomial, and it's known that it has positive coefficients. Don't know how to do this. Finally, here's a generalization of the ASM problem in terms of quotients of specialized Schur functions. You take a Schur function of a multiple of a staircase divided by another Schur function, a multiple of a staircase. That actually is a polynomial, that's been proven, but it's conjectured to be a positive polynomial. And if you take p equal 2, you get alternating sign matrix numbers. N equal 2, you get the Catalan numbers. So this is a way of generalizing ASM and Catalan to two parameters, N and P. Problem 10. What does this quotient of specialized Schur functions count? We don't know. And in fact, if you don't like those Schur functions, you can put in the factorials instead. So you could just forget about Schur functions. You just say this quotient of products of factorials. It's known to be an integer. The Q version is known to be a polynomial, but it's conjectured that it has positive coefficients. We don't know that. We do know that for the ASM case, because the ASMs are equinumerous with descending plane partitions, And George proved that the right-hand side is the generating function for those descending plane partitions. We don't know what these things count. That factorial. Thank you very much.
Thank you, Professor Stanton, for a very interesting talk. Lots of very nice problems. Are there any questions? So I had a couple of questions. So one thing you discussed these type R1 orthogonal polynomials. Does an analog of Favard's theorem hold like the converse for these type R1 and R2?
I don't think that's been worked out. Like, I don't know what the conditions are that gives you a positive measure. You always have linear functional, but positivity for a measure, I don't think that's been worked out.
Okay.
Almost nobody has studied these polynomials besides Morad's original paper with David Masson and these recent papers we did. There's a few others. There's Zhadanov has certainly studied these. So there are a few other things, but I don't know about that Favard type theorem.
Okay. And my second question was, you started with this McMahon's combinatorial interpretation of Rogers-Ramanujan identities. So if you go to Andrews-Gordon, and if you look at the multiple sum side, the Andrews analytic version of the generalization of Rogers-Ramanujan, that multi-sum combinatorially interpreting this one side of Gordon's interpretation, that you take parts which are of the form bi and bi plus k minus 1, that gap is at least 2, and
Yes.
some more restrictions. So is there somebody who has directly proved that multi-sum combinatorially interprets this side of Gordon's combinatorial version? Because when I looked at Brasu's proof, it is sort of a mix of analytic and combinatorial techniques. He does some combinatorics, then proceeds by induction, and then he does it for all k. But is there any direct combinatorial proof there itself?
I don't have a definitive answer, but two people that worked on very similar things and may have answered that are Jean Douce from Switzerland, and then the Turkish student, man, I hope I pronounce his name right, Kurdandoz.
Okay.
The Turkish student, maybe you know him.
Khan Kursungos? Yeah.
Yeah, he was a student at Penn State, I think.
Right.
Probably just before you, or maybe around the time you graduated. So they both have ways of thinking about those multi-sums.
Oh,
Also, Ole Warner has a way of thinking about those multi-sums in terms of multiplicities of the partitions instead of the differences, additions of the multiplicities. So it may be that, yes, they have an answer to that, and I just don't happen to know or remember. So I apologize.
okay. So,
By the way, what I did with the Rogers-Ramanujan, we also did for Andrews-Gordon. You can insert those rational functions and get generalizations of Andrews-Gordon.
and is it in the same paper, Refinements of the Rogers-Ramanujan Identities?
Excuse me?
Is it in that same paper, Refinements of the Rogers-Ramanujan Identities?
Yes, refinements and shifting. Yes, it's called marking and shifting.
Oh, okay.
Called marking and shifting in partitions. So not only we did Rogers-Ramanujan, but we did other ones too. In fact, I wrote down some general theorem that if the sum side looks like a certain sum, then you can always do this inserting of at least one factor. I don't know how to insert more than one, but you could always insert at least one factor.
Okay.
That's
you.
in that.
Uh-huh. Uh-huh.
Probably not a paper many people know, but I think it's in experimental math.
Okay. Okay. Sure, I'll take a look. Thank you very
Thank you.
much.
I have a question,
Yeah.
Dennis.
Yes.
So you showed some transformations of continued fractions on transformation. And
Yes.
so my question is, so Ramanujan in his lost notebook has the slightly general version of the Rogers-Ramanujan continued fraction, and that's written as so there's a series over a series equal to a continued fraction, equal to another continued fraction, equal to a third continued fraction. And it has one more parameter than the Rogers-Ramanujan identity. So is that, I mean, is that something explained by this theory, or have you considered that?
No, I haven't considered that at all. No, I don't know that. That would be very interesting if that came from. I know that the original Rogers and Ramanujan, there are orthogonal polynomials behind that.
Yes.
But I don't know about type R1. That would be very interesting to find that, to explain that.
Okay, thank you.
Go
Yeah.
do it. I don't know.
Yeah, I could write to Murad.
Any other questions? Yeah. If not,